Hi, so I worked on the Raspberry Pi. So the Raspberry Pi essentially acts like a hub between various devices. So if you're familiar with the client-server architecture, the Raspberry Pi acts like a server where various clients such as the Android tablet or the PC or the Arduino connect to the Raspberry Pi. So essentially it acts like a central hub. To implement this, we have used a multi-threading concept where one thread has been allocated to every device of the client which is connecting to the Raspberry Pi.
I did image recognition for MDP, so what I did first was I had to crop out the 15 templates, one for each image, following which I would then implement HSV segmentation. So HSV segmentation will be able to segment out images of different colors. So since we have 5 different colors, I will perform HSV segmentation 5 times for each video frame that comes in to the RPi. After segmenting out the image of the specific color, I would then perform template matching for each of the templates of that color.
After the assembly of the robot, one of the main challenges the Arduino team had to face was the straight line motion. The issue arises when the RPM of one wheel is different from the other. The solution implemented was a closed-loop PID system where each cycle, the Arduino takes in the previous RPM and decides the correct speed for the next cycle to give the correct RPM for that cycle.
The other main challenge faced by us Arduino team is the inconsistent sensor values. The sensor reading have to be accurate in order to properly gauge the obstacle distance from the robot. However, due to various reasons such as inconsistent battery output, the sensor readings may not be accurate. This may result in the robot crashing into obstacles, or the robot may detect something as an obstacle when there's actually nothing there, which is also known as phantom blocks. We spent quite some time trying to solve this issue and eventually overcome it by acquiring multiple readings before selecting the mode as the most likely and optimal reading.
The fastest path algorithm we used was A*. However, the basic A* algorithm could cause staircasing effect. So we added some changes to A* such that it reduces the amount of turning during the run. We also made some changes to the way commands are issued to prioritize faster timing for the fastest path.
Lastly, the algorithm team is responsible for creating the brain of the robot. For the exploration, the algorithm team implemented the right wall hard algorithm with some enhancements. These enhancements were added to resolve the 3 main issues we encountered, that are inaccurate robot movements, phantom block, and infinite loop on phantom block removal. With these enhancements, our robot was able to achieve 100% exploration coverage.
For the Android application, we are able to display grid map based on what the robot explores with the help of the exploration and fastest path button. Our intuitive user interface has all controls in one place, providing ease of use and convenience. Instead of typing the X and Y coordinate for our waypoint, the waypoint setting is also done through the main page by clicking on the button and touching a cell on the map. If it has been set wrongly, we can always touch on the erase button to erase the current waypoint.
Obstacles can also be plotted in the manual mode in the same way that the waypoint setting is done. These are the unique features of the Android application. The main function of the manual mode is that it enables us to debug various scenarios of the robot exploration. Bluetooth connection with the Raspberry Pi and the message passing can be accessed via the action bar at the top right corner. The most important thing during the competition is the Bluetooth connection. We have ensured that the Bluetooth connection is robust by making sure it doesn't crash when connection is lost.